Απλά να σας πω, κύριε Κρυμιζή, ότι περιμένουμε ακόμα ένα πούλμαν με γύρω στα 25 παιδιά, γι' αυτό καθυστερούμε.
Δεν έχω πρόβλημα.
Μας είπαν ότι είναι στον δρόμο, έρχεται. Γι' αυτό,
κανένα πρόβλημα.
Εδώ οι δρόμοι είναι αυτή τη στιγμή σε λίγο άσχημη κατάσταση και υπάρχει μεγάλη κυκλοφοριακή συμφόρηση στους δρόμους. Ζητάω συγγνώμη και την υπομονή σας.
I can imagine πώς είναι.
Μόλις φτάσανε, κύριε Κρεμιζή. Σε 2 λεπτά
Ναι,
ξεκινάμε.
Βλέπω ειδικότητα. Ναι. Πώς είπατε. Ευχαριστώ.
Okay, so I think we are ready. Good evening, Professor Krimizis. It is my special honor to have you with us in this second International Olympiad on Astronomy and Astrophysics for juniors. And I think that it is very, very pity that we don't have you here in our city with us. Anyway, modern technology permits us to have this connection via internet. So, although I'm so sorry to not having you here, it's better than nothing at all. And so, instead of, I had prepared a long biographical note, but since we don't have, we are a little bit late in starting this presentation and this very nice speech. So I will say a few words about you. So good evening also for you and the citizens here of Volos. Professor Krimizis was born September 10, 1938. He's a Greek-American scientist in space exploration. He has contributed to many of the United States unmanned space exploration programs of the solar system and beyond. He has contributed to exploration missions to almost every planet of the solar system. In 1999, the International Astronomical Union named the asteroid 8323 Krimizis in his honor. I think it was the shortest introduction that I could find for you, and we are looking forward to your presentation.
Well, thank you very much, Professor Zachilas, and I thank you and the organizing committee for inviting me. I'm really sorry that I cannot be with all of you today. Believe it or not, this week may have been difficult for all of you visitors, but actually Volos is a beautiful city. I have been there several times, and I also express my regrets that you have been here in such an extreme weather event. I hope it will be a unique event in global warming, and that you will never experience the effects of global climate change in your lives. And I say that as a forlorn hope, because it may not turn out to be that way. So today I would like to talk to you about Voyager. As you know, I have already discussed this topic many times before, and there is always something new about Voyager. And what you see in my initial background image, you will see again repeatedly, and I'll tell you why. Here is my title, 46-year Odyssey of the Voyager missions from Earth to the galaxy and the future of interstellar probe. I believe you're all familiar with the word Odyssey. It's a part and parcel of being in Greece and in our civilization. So I will spend only a little bit of time, but any mission that is launched to space and lasts 46 years has to be a very adventurous mission, just like Ulysses in the Odyssey. So begin by the outline about our position in the galaxy, although I know you know it well. The Voyager missions, I'll talk about the heliosphere, only a little bit about the space odyssey, the probe. So our position in the galaxy, you know it well, but I thought I would mention again that, and we look at a clear sky. I don't know if the sky is clear in Volos today, this evening. As we, as you all know, are sort of the model that shows many of us. Here's myself. I was the youngest principal investigator at the time. So now, okay. I don't understand why. Okay. Do you see the slide? Okay, good. So, why was it possible to do 4 planets? It turns out that every 175 years, the outer planets line up on basically one side of the sun. And one can use the gravity of Jupiter to accelerate the spacecraft to go quickly to Saturn, and then from Saturn to Uranus and Uranus to Neptune. We decided to send, after Saturn, the Voyager 1 above the ecliptic plane. I will explain that. But Voyager 2 visited Uranus and Neptune, and they went to the south ecliptic plane. And if you want to read some details, there's a paper in the American Scientist by Rob Decker and myself that explains more detail. However, let me show you how this effect of gravity assist works. When we launched the spacecraft at Earth, it was at about 36 kilometers per second from the launch vehicle at Titan Center. And as you can see, the velocity of the spacecraft began to drop quickly because, of course, the sun was pulling the spacecraft back, solar gravity. However, when we got to Jupiter, you see that we went from 10 kilometers per second to 26. In other words, the gravity assist from Jupiter accelerated the spacecraft by 16 kilometers per second. Then we left Jupiter. Again, the solar gravity slowed the spacecraft down, but not at higher rate. And then at Saturn, we did the same thing. We accelerated the spacecraft. We gained about 15 kilometers per second. And now from Saturn to Uranus, solar gravity is very weak. We went there to Uranus, we accelerated again. And after that point, we didn't have much work to do, so to speak. We visited Neptune, and now the spacecraft is moving at about 15 kilometers per second. This dotted line that you see, by the way, is the solar system escape velocity. In other words, any spacecraft that, say, at 20 astronomical units, if it's a little over 12 kilometers per second, it would escape the solar system. And of course, Voyager 2 is at 15 here, Voyager 1 is at 17. So these spacecraft will forever travel unaffected by solar gravity, and it will be, if you like, billions and billions of years, as Carl Sagan used to say. So once we went past Neptune, NASA was persuaded to declare the Voyager Interstellar mission. What did that mean? It meant that we were going to try to find out where the edge of the solar atmosphere was, the solar wind. Where did it slow down and where did it totally stop? And finally, where is the border between the solar atmosphere with the galaxy? And this is shown schematically here. So that's the rest of the story. But I thought I would show you what a spacecraft looks like. And this is the Voyager spacecraft at the Jet Propulsion Laboratory in Pasadena. I'm standing next to it so you can get a sense of the scale. The instrument is the one that was built by my team and myself. It's called Low Energy Charged Particles. At that time, we didn't know how to make up nice, cute names. And I'll tell you a little bit about the specifications. So weight, it's a little less than a ton, 825 kilograms. When we started out, the power was 465 watts. We have a radioisotope thermoelectric generator that works with radioactive plutonium. But now, after 46 years, go down to near 230 watts. We lost about half the power, which is the half-life of the plutonium. Diameter of the antenna is 3.7 meters. The power of the radio from which we send data to Earth is 22 watts. And we have plenty of hydrogen fuel. So that's the spacecraft. The five rather instruments that are highlighted are the ones that are now working on Voyager, and because the others are of no use in their planetary and interstellar space, we don't need cameras. We needed some UV spectra. We cannot afford the infrared measurements. And these are the instruments that are doing the exploring now. And this is the instrument that the team that I work with is. And notice it's hanging on this boom, and the spacecraft antenna is always pointing to Earth, which is where I have the pointer here. Now, if you want to really look around the sky, the spacecraft doesn't rotate, so you have to rotate it yourself. And I thought I would show you the instrument.
This is a scale model of the Voyager 2 spacecraft that is presently in the process of flying by the planet.
Okay, I'm not going to bore you, but what you heard was a stepper motor that rotated the platform with the instruments 45 degrees every 192 seconds. And we estimated that we needed 250,000 such steps to go from Earth to Jupiter to Saturn, the original 4-year mission. I have to tell you that now, of course, 46 years later, this stepper motor has been stepping continuously, and it has gone 8.5 million steps so far, and still working, which is an amazing occurrence because none of us, including my engineers, ever believed that it would work that long, and they did their best to persuade me not to use it in the design. So, but let me tell you about the planets here. I'm not going to get into the planets because that's not the point here. I just want to tell you, of course, that these all are the images that Voyager took, but I will say a couple of things only about the so-called red spot on Jupiter. And this is a highlight of the red spot. The Earth fits, 2 Earths fit into this red spot. An Earth diameter is about this much. And more importantly, the Galilean satellite, Io, Europa, Ganymede, and Callisto. And they all have different colors for good reason. Io is volcanic. It has 13 active volcanoes that are going continuously. The biggest one is 10 times as big as the biggest volcano on Earth. They get to an altitude of like 300,000 kilometers. And it's the first time that we knew as a human race that there are actually volcanoes outside Earth. And so this is only one of the main and important discoveries of Voyager. Europa, as you know, has a shell of ice and an ocean of water underneath, and so on. I just want to tell you that Voyager made a lot of discoveries in the outer planetary system. So let me just say a few things about the environment of the heliosphere here, because it's important as to where the Voyagers are. This shows, of course, the sun in the center, the orbits of the planets, and it schematically shows the solar wind. The solar wind, which is a gas that is emitted by the sun, and I will show you a schematic in a minute. The Voyagers, well, outside the solar atmosphere of the solar system, in the galaxy, there are cosmic rays. Cosmic rays, as many of you know, are very high energy particles. They travel with the speed of light. Some of them get into the solar system, but not as many as would get in had there not been the solar magnetic field. And by the way, from where the Voyager 1 is now, out here, to Earth, the signal takes about 22 hours and 22 minutes, moving at the speed of light from Earth, from Voyager to Earth. So we get data after 22 hours and 22 minutes because Voyager is at a distance of 24 billion kilometers. Now, I want to show you this little video that shows the sun, solar activity, and the solar wind. You see, the solar wind continuously comes out of the sun, has a very high temperature, about a million degrees Kelvin, and it moves at a very high speed. Here is a schematic representation of the solar wind. The solar wind goes past every planet of the solar system, and eventually slows down. And at some point, it kind of runs out of density and speed, and it's pushed in and limited by the galactic magnetic field. This is the only data I will show you from Voyager. This is a plot that shows the intensity of ions that we measured in 1977 when we launched. This is a logarithmic scale, and for until about the year 2002, the intensity dropped by several orders of magnitude, and then all of a sudden we saw the intensity increase again. That was the time when we crossed the termination shock of the heliosphere, and as you can see, we went up by a couple of orders of magnitude, and then after a few years, these particles disappeared altogether. And then we did the same thing with Voyager 2, where we later crossed the same termination shock, and then after about in 2018 actually, we dropped again. So, but what I wanted to show you more is what happened to the cosmic rays. So from 1977 to 2020, you see we went through 4 solar cycles, each of them roughly 11 years. The cosmic rays started from about this level close to Earth. And now they're up to this level, which is 7 times more, which is the point that I tried to make earlier, that the solar magnetic field shields our Earth from galactic cosmic rays, from galactic radiation. And that has effects on the bioevolution of Earth activity over the several billion years. Okay, so when we crossed the termination shock with Voyager 1 at 94 astronomical units, it was on the cover of Science magazine, then with Voyager 2 at 85 astronomical units on the cover of Nature. But the question was, okay, so here's the termination shock. Here's the schematic that I'm showing you. Question was, well, how far would it be before we actually crossed outside of the heliopause and into the galaxy? And what we discovered was that at some point at 113 astronomical units, the solar wind stopped expanding radially. It just stopped dead on its tracks. And we published that back in 2011. And we made some calculations, and we estimated that the heliopause would be crossed in July of 2012 at 121 astronomical units and 18 billion kilometers. And sure enough, it turned out that Voyager crossed in August of 2012 at 121.6 astronomical units. So this is a little video of what we have found so far. So you see here the particles that are pink represent solar wind and solar particles. And now and then you see that once we cross the termination shock, you see these blue particles, more cosmic rays coming into the solar system. And then at some point, when we cross the heliopause and went outside into the galaxy, the only thing that was left were cosmic rays. The pink particles, the solar wind, all disappeared. I want to show you this picture simply because we all got together with the Voyager team and tried to decide what it is that we saw. Did we actually get outside the solar system into the galaxy or not? And there were considerable discussion about whether that was a true crossing. We actually decided that in fact it was. And this is, again, a cover of Science magazine back in 2013 with 4 papers, each explaining the observations from the low energy particles to the magnetic field, to the cosmic rays, and to plasma waves that were observed. So just to show you what it looked like when we crossed with Voyager 2, for example. This is galactic cosmic rays, okay? And down here are solar particles, we know from the composition. And you see that when we get to this point, this is from Voyager 2, November 5, 2018, the galactic cosmic rays go up because the galactic cosmic rays come from the galaxy, obviously. The solar particles disappeared. In other words, it's a very clear-cut signature that we crossed the heliopause and we are into the galaxy. And again, there was a special issue of Nature, Astronomy magazine, talking about the fact that Voyager 2 breaks out of the bubble after 41 years of travel and nearly at the same distance as Voyager 1 did, Voyager 2 at 119 AU. So about the same. So when we put all the data together we came out with this composite figure schematic that shows you what the heliosphere looks like. The sun is at the center. These are the orbits of the planets, the Voyagers that went up, one north and one south. The helioseed, which is full, is a reservoir of energetic particles and plasma with very weak magnetic field. And then we cross into the galaxy and we only see cosmic rays now. But we also heard something else, and I will play that for you. It's plasma waves. That is from the antennas of Voyager, and you can see that we generate, the plasma waves are generated at about 3 kilohertz and propagate in the galaxy. And they happen occasionally, like maybe every year or year and a half. And the reason is that every now and then the sun sends out a terrific blob of plasma called the coronal mass ejection. And it goes at a speed of like 1,000 or 2,000 kilometers per second. However, it takes it about a year and a half before it reaches to the outer heliosphere, cuts through the heliopause and comes out into interstellar space. And that's where we hear the sounds, because low energy electrons begin to gyrate up around a very strong interstellar magnetic field. And we record that sound. Now, how big is our solar system compared to, for example, the black hole that was identified in M87? And I have placed here, here is the sun at the center, Pluto's orbit, Voyager 1 is out here. In other words, our entire solar system, with all the planets and much beyond, is about the size of the black hole in M87. However, the black hole in the center of our galaxy, which was identified through the Event Horizon Telescope, is a lot smaller. This is the orbit of Mercury. So this is just to get a scale of the distances. Now, I would tell you one more thing here about, we had lots of adventures with Voyager, and I could spend many hours telling you about the problems we have had. And so I'm going to just tell you one thing about the latest problem. Can we lose a spacecraft? Of course we can, and all it takes is a mistake. This is from the New York Times on July 21. Engineers on the ground sent an incorrect command to the spacecraft on July 21 that knocked its antenna 2 degrees away from Earth. Needless to say, when that happened, we lost signal, and we were wondering whether the spacecraft will continue to work and whether we are going to recover it. So by August 1, there was another story in the New York Times. NASA's Voyager 2 is out of contact, but not lost in space. And the reason for that was that we asked the Radio Astronomy group to search the sky for the Voyager signal. And this is the plot of the signal from the vicinity of where Voyager was. And I don't know if you can see this. This is a line. It's only a few tenths of hertz wide. Mind you, this and even the whole signal was plus and minus 400 hertz around this line. The signal to noise was 0, but nevertheless, it was the right frequency. So you're talking about picking out a few tenths of hertz out of 2,800 megahertz. And we knew that Voyager was alive, and all we had to do is send a corrective command to point it to Earth. So NASA used the biggest transmitter it had in the Southern Hemisphere, and it sent a fairly broad command. Again, it was described in the New York Times as a last-ditch shout across the void on 4 August. And when, lo and behold, the command was received and Voyager turned its antenna back to Earth. So we lost data from July 21 to 4 August, but we still have the spacecraft and it's working fine and we're getting data every day. In fact, I looked at the data this morning and it was wonderful. So these are some of the trials and tribulations that these spacecraft have gone through. And that's why I like to call this mission the Odyssey in space of the 20th century. Now, what about the future? The batteries, as I said, are radioactive plutonium and will last about the year 2028 or so. So the last 3 years, we start deactivating instruments from 2020 at about 150 astronomical units. Now, you might say, what does deactivating mean? What it meant is that we had heaters that kept the instruments warm so that they can work properly. And we had to turn off those heaters, whereupon the temperature of the instruments, in my case, the low energy charged particle instrument went from 12 degrees to minus 40 degrees centigrade. And believe it or not, it's still working. Similarly for the other instruments. So in spite of the fact that we're now operating at temperatures which are far below anything we tested the instruments for, they're still working. And by the way, remember the little stepper motor I told you about that rotated every 192 seconds? It's now at minus 62 degrees and is still working. That's something that I was absolutely amazed. I never expected that. So as of now, the last instruments that will stop operating at about the year 2030 at about 185 BU, 28 billion kilometers from the sun. Now, as I said before, the Voyagers have escaped the solar system. Therefore, that means that they will continue to move forever. And in fact, Voyager 1, in about 40,000 years, will go by the Camelopardalis constellation at a distance of about 1.7 light years, whereas Voyager 2 will pass by Ross 248 in Andromeda, in the constellation of Andromeda, 1.7 light years, but in 296,000 years will pass within 4.3 light years of Sirius. So that is the messenger that humanity has sent into the cosmos, but it has sent also something called the golden disk. This is my colleagues Dan Garnett from the University of Iowa and Ed Stone from Caltech. And this particular disk was actually designed by Carl Sagan and his colleagues, and it includes messages from humanity, including pictures, symphonies, songs, the DNA of a human being, and this is the cover that covers this disk and shows from the directions of several pulsars where the Earth is. And it's all coded in the wavelength of hydrogen, on the presumption that any extraterrestrials who capture Voyager will have a high enough level of civilization that they would know immediately that the most common wavelength in the universe is what they should look for to decode it. And here's, of course, Carl Sagan, which, as I said, designed this, and unfortunately he passed away in 1996. And it has all kinds of sounds and also greetings from well, probably not every language, but about 90 languages of the world, including one in Greek, which I will read to you in Greek. You may not understand it. Ήτινες ποτέστε χαίρετε, ειρηνικός προς φίλους, ελιλήθαμεν φίλοι. And it says, whoever you are, greetings, we come with peace in mind to friends and greet you as friends. So much for the message that we sent to the solar system. There is, by the way, a documentary for the Voyagers. It's called The Farthest, up here. and it was produced by the Crossing the Line Studios of Ireland. It got the Emmy Award in 2018 in New York, and you can actually watch it on YouTube. I have put in the link, but I think if you just go to YouTube and write the farthest, it will show it to you. It's a fairly long documentary, over 2 hours, but there are shorter versions as well. So it's a very interesting story about Voyager. Now, you might say, how far have we really traveled with the Voyagers? And I thought I would do an analogy with the Olympic Stadium that we have here in Athens. And I put the sun at one end. And then when you do that, the Earth is a little dot nearby. Here is the orbit of Saturn. There is the orbit of Neptune. And here is the heliopause, the exit to the galaxy. And here are where Voyager 1 and Voyager 2 are now. So you might say, well, how close is the closest solar system to our own, namely Alpha Centauri, which, as we know, also has exoplanets? Well, it's in Sofia, which is in Bulgaria, the capital of Bulgaria. So you can imagine about the distances and how far things really are in space. You are studying space, I'm sure you know all of this, but here's what I put together just for a general audience. So the distance to Alpha Centauri is 41 trillion kilometers. As I said, is 2,000 times as far as Voyager. A trip with the speed of light, of course, we don't have any such spacecraft, would take 8.7 years round trip. And it's technologically impossible. With a spaceship at the speed of Voyager, which is 70 kilometers per second or 61,200 kilometers per hour, that would take one way 78,000 years. So what is the conclusion? We should forget about colonization, no matter what Elon Musk says. And the solution is to protect the Earth at least for the next few hundred years. It's the only spacecraft we got, and we are the passengers. If we destroy it, I think the human race is going to be finished. So let me just say a couple of words to conclude about the Interstellar probe. We just completed the study at the end of the year, of the last year. And this is the conceptual spacecraft, the Interstellar probe. And one of the things that I didn't point out as strongly as I should have is that science is built up of facts, as Poincaré said, as a house is built of stone. But an accumulation of facts is no more a science than a heap of stones is a house. Why do I say this? I'm saying this because the direction and the distance and the characteristics and the properties of the heliopause and the termination shock and the interaction with the galaxy and the magnitude of the magnetic field and the direction of the interstellar magnetic field that had been predicted by models were wrong, absolutely wrong. And we need to keep bringing the facts to really know what is actually happening. And it's in that spirit that the idea of an interstellar probe was generated. We just finished the study, as we said, for NASA. This is the conceptual spacecraft with all the instruments. I'm not going to bore you with that. I will just say that there are questions left. What is the nature of the interstellar material around our sun's atmosphere? How do the sun and the galaxy affect the dynamic heliosphere? So I showed you how some coronal mass ejections get to interstellar space and generate waves. What is the structure of the heliosphere? And where did matter come from and how did it evolve in our solar system and the interstellar medium? We don't have answers to these questions. And that's why we need to delve deeper into the galaxy. I'm showing you this little video because it shows how my colleagues and how science works. This is the conceptual framework for the interstellar mission. One figures out how much energy you need, whether you need the gravity assist. This is, for example, the spacecraft after it was assembled, and it will be launched by the Space Launch System because it needs to move at a much higher speed than Voyager did. This is the same rocket, by the way, that went to the moon last December and came back without the astronauts, of course, without astronauts. But its evolved version is the one that will be used to shoot the Interstellar probe into space. It will get a gravity assist from Jupiter, just like Voyager did, and other missions like Cassini did to go to Saturn. And eventually, it will get outside our solar system and move very, very quickly. And it will get to past the heliopause and past the termination shock in about half the time that Voyager 1 and Voyager 2 did. And you can see it schematically here, how it's now going to move to as far as 1,000 astronomical units. And I can't finish without telling you about the other end of the spectrum, which is the Parker Solar Probe, which is the origin of and the pinnacle of our solar system. This is an actual image of the sun. And I'm showing you that which occurred in August of 2018 with the Parker Solar Probe. This is the spacecraft, of course, and you can see the deployment. Studying the sun very close. It gets very close to the sun. The heat shield will get to about 1,400 degrees centigrade. And it was all achieved by a launch from Cape Canaveral and by a gravity assist from Venus this time. And what that did is change the trajectory of the spacecraft to bring it closer to the sun. And you can see this particular one, for example, you see, and it comes closer, closer, and closer. And it will get, it's already to within 8 million kilometers, about 19 times the intensity of the sun as at Earth. It will get to 6.1 million next year. And when it goes through perihelion, it moves at the speed of 700,000 kilometers per hour at its closest approach. So that is the Parker Solar Probe, 6 million from the solar surface, 0.04 astronomical units. Voyagers 1 and 2, 24.1 billion kilometers, 160, 161 astronomical units a day. And we are aspiring to do the Interstellar Probe, which could go as far as 150 billion kilometers in the future. So, Parker Solar Probe, mission to touch the sun, and the Interstellar Probe to the stars. And the real journey has just begun. And it is you, the young people, who are going to implement that. This is a little video that shows the hope for launch of the Interstellar Probe in the mid of the next decade that will go past all the planets and eventually get out into the galaxy beyond the solar atmosphere and do so in a record time compared to what we did with Voyager. So, as the poet said, but a man's reach should exceed his grasp, or what's a heaven for? That's from Andrea de Salto by Robert Browning. And then Edgar Allan Poe said, is all that we see or see but a dream within a dream? These are the websites in case you want to look things up. And I thank you. I hear nothing. I hope you did hear me.
We heard everything.
Yes, everything was clear, and we were listening very carefully to all your speech. Thank you very much for your very, very interesting speech. Would you mind if I ask the audience if they have a question or two before we stop our...
I'll be very happy to answer any questions they have.
So if someone wants to ask Mr. Krimizis for something about the past mission or the future mission, okay. Let me bring the microphone up there.
How much energy have the Voyagers now? How far can go?
The Voyager, of course, doesn't need any energy to keep moving because, as we said, it's escaped the solar system. However, the problem is the batteries. And the batteries from radioactive plutonium have a half-life of 84 years. And we're now down one half-life, so we have 230 watts. The spacecraft cannot really operate much below 220 watts, and we're losing a couple of watts a year. So what will happen is that the way the spacecraft is pointing to Earth is by control jets at the edge of the antenna that are fired by hydrogen gas. The temperature of the hydrogen tank and the tubes inside the spacecraft are at about 2 degrees centigrade. If the temperature drops to zero, they will freeze, and they will no longer be able to point the antenna. And at that point, we'll lose communication. So we expect that that is going to happen between 2028 and 2030. That's how long.
Okay, thank you.
Next question.
Yeah, hello from me too. I want to ask something about how to launch a rocket, for example. Why don't we make a launch pad in space in order to avoid the gravity of Earth? I know that it costs a lot of money, but we in my opinion, we can succeed in a very large speed, let's say.
Well, in a way, that's what happens, because when we launch a spacecraft from Earth, then we put it into orbit around Earth. And then we fire the second and the third stage to get away from Earth. Now, to have a launch pad in space, as you put it, you have to carry a lot of fuel up there. And you have to assemble a rocket up there. And all of that, of course, takes additional rockets and additional lifting, and it's very expensive. So it's an obvious thought, but it's not easily doable. Perhaps someday, when you all grow up, you figure ways to build rockets on the moon, and then shoot them from there, and that will be able to avoid a lot of the Earth's gravity well. But right now, the technology is about as good as it can get, and that's the best we can. And that's why, for example, the Artemis project, which will take people to the moon and back, is still, in a way, the old-fashioned way. It's just a bigger rocket than Saturn V. That's all.
Thank you.
Next question. No one. Okay. So I think that we have to stop now, since there's no other question. We would like once more to thank you very much for this excellent presentation and your that you shared with us. You shared your dreams of 1976, which are still alive, and that what I said to these young students, that they have to follow their dreams and make them be alive as much as they can, if it's possible. Perhaps someday the extension or the dreams that we have now be alive for much more time than we have originally thought that would still be. Like Voyager. I think that Voyager was just for a couple of years. And after so many years, it's still alive, transmitting data back to Earth. It's a miracle, I think.
Absolutely, it is. And the people who build it and who build the instruments are more amazed than anybody else. And this generation, the young people you have in your auditorium today, they're the ones who have to make the Interstellar probe possible. And that mission will last 50 years as well. That will be designed to last 50 years, which means that one has to have succession plans. And it's not only these young people, but their children who are going to have to receive the knowledge that is generated to continue the program. It's a multi-generational effort, and it's a very nice thing to look forward to. And again, thank you very much for inviting me.
Thank you also very much. Okay, that's all, folks. So our next step is to follow our dreams, to eat some.